maybe I can start. So this is our last block of 4 lectures. And let me just outline, oh, why is that color? Huh. Oh, it's, does that look pink? It looks sort of pink? No. Is it white? Okay. Outline of this block of lectures. First of all, I want to review the certain neighborhood. It's a funny formulation of holonomy. So in other words, what's really going on with holonomy and the importance of holonomy and how Cartan understood these. And then I want to at least state the classification of Riemannian manifolds. State is a word we should put in quotes because it, well, no, what we should put in quotes here is the word classification. Riemann manifolds based on holonomy. In particular, to state without proof Cartan's basic, what maybe I'd like to call dichotomy. I know your English is not, do you know the word dichotomy? It means either or, one or the other. So it's a very, it's also a German word, right? More or less. So based on holonomy. And what this leads to is the study of locally and globally symmetric spaces. I'm going to discuss these things in some detail. This requires, in particular, some background on Lie theory. I know that Kayvon in the last semester mentioned a little bit about Lie groups and so on, but we'll discuss a little bit more. Okay. And then finally, in this block of lectures, which is finally the main 3 examples in dimension. So the details the main three examples. Since it's the only three examples in the two-dimensional case, in dimension 2. And in terms of their constant curvature examples, so it's two-dimensional. Recall that there's something called a curvature tensor, which I'll remind you of what it is, but this means sectional curvature is the same thing as curvature. And so you can talk about constant curvature, and so these will be a constant curvature. -1, 0, and +1. Okay, you could have -2, but we can scale the metric. You understand, you can always scale the metric by a constant and you change nothing. Right? So these are the basic things, and -1 is the unit disk with what is normally called the Poincare metric. And 0 is just the flat plane. And +1 is the sphere. And identified with P1C, which is equipped with the Fubini-Study metric. So with Fubini-Study metric. So these are the constant curvature things. These are the simply connected. These are the simply connected ones. Globally symmetric spaces. Dimension 2. And many of you were in my course last semester in complex analysis. You see these things, of course, appear in complex analysis. This is, in some sense, the uniformization here. So if M tilde is either the disk or the plane, let me even write it here in complex analysis of P1C, then M is M tilde modulo, let me even write it explicitly, modulo the fundamental group. And as you know, the fundamental group in the compact case is of course trivial because every automorph is so for M equal P1C, let's emphasize that that is equal to the sphere. Every automorphism has a fixed point here, has a fixed point. Has a fixed point. And therefore, pi 1 of M in this case is trivial. So, I mean M tilde modulo the fundamental group. No. M tilde is so there are three. Let's write the notation here. So the detail of the main three examples in dimension 2 of constant curvature, and well here let's write it here. This is pi 1 trivial. Right? And now in general, if you have a general M in dimension 2 with constant curvature metric, then M tilde is going to be one of these, and M will be just M tilde modulo the fundamental group. Okay, you okay on that?
Yeah. So you're treating the manifold as a Lie group of sorts, and then you take that. Because for any, so you're treating the manifold as a Lie group, right?
No.
You mod out.
Nothing is here a Lie group.
So
Well, this is a Lie group.
Right. How do you mod out then?
So is the covering group. So maybe let's. So it's good you ask these questions because it's sometimes just notation, right? Recall pi 1 n acts freely and properly. I'm going to review this notion of proper action on the universal cover. M tilde of n. Okay. Some people call that the group of deck transformation. I know, it's just a free proper action of the group. Okay, so that's in general, and in the case of the sphere, so this is, this is the case of the sphere, so this is +1 curvature, constant curvature, minus 0 curvature, yeah, then M is equal to M tilde, and in this case you're okay with it because it is the plane, and this is thought of as an additive group, and it's the plane modulo, let me write it here, gamma. So where gamma is a lattice as a discrete additive subgroup. The word lattice is a little bit dangerous because it has other meaning. Discrete additive subgroup. Rank 1 or 2. Well, or 0, 1, or 2. So it could be trivial. So for example, if the rank of gamma is 2, then gamma is equal to n omega 1 plus m omega 2, where n and m are integers. And you did this when you were a child with the parallelogram, you did this omega 1 and omega 2, right? And when you were a child, you say, well, you do this, and then you identify that with that, at least I did, right? And you identify that with that, and you get the torus, right? And now I purposely just made a mistake. There's no such thing as the torus, because the torus definitely depends on omega 1 and omega 2. The metric definitely depends on omega 1 and omega 2. So you take the flat metric on R2, you make the quotient, and you ask when are these two quotients, you make two quotients, say, so you make another one like this. Let's say here, this generates gamma hat, and this generates gamma, yeah? And so then you ask the question, so you say M is equal to M tilde, so the plane, modulo gamma, and M hat is equal to the plane, modulo gamma hat. Right? And you think they're the same, because when you were a child, you took that with scissors and you cut that like that, and you cut like that, and you first made a cylinder, and then you hook these two things together, right? Yeah? And the theorem is they are the same if and only if they are complex analytically the same. They are metrically the same if and only if they're complex analytically the same. So they're very, very rarely the same. What does the same mean? The same means isometrically equivalent. It's completely clear what I mean by isometric, right? So, right. So the same means there's a mapping phi from M to M tilde or vice versa, I don't care, M tilde or M hat, which is a diffeomorphism, so which is isometric. So phi star of G hat equals G. Okay. Very rarely the same. They're the same if and only if they are complex analytically the same. Very interesting. The complex analysis situation here is identical, basically, to the. And now -1. From my point of view, this is not so difficult. Tori are interesting and so on. And the sphere is interesting and so on. But -1 is really interesting. Negative curvature. This is called, so delta, which you maybe want to write as H, the upper half plane. You like it more maybe as the upper half plane. It's the same. It's called the hyperbolic plane. And we will see, there's a very beautiful picture of this thing that maybe doesn't look so linear. You maybe like to embed it some way nicely. If you take a cone, if you take a certain light cone in R3, so you take a light cone in R3 and then you will see that this will be in a very natural way M tilde, the hyperbolic plane. I will explain that later on, but this will be the hyperbolic plane equipped with a natural metric coming from the ambient space. Hyperbolic plane. So this has negative curvature, and then this is M now, M tilde. Okay, it's simply connected. Anybody understands that's simply connected, it's contracted. And now M, any M, is M tilde modulo whatever this pi1 of M. And pi1 is of M is now a discrete subgroup of the isometries of M tilde. Yes, it's acting by metric preserving mappings, and it's discrete because it's a covering transformation. You all had a little bit of homology, so you should know this. Yes? So, yes, these are the deck transformations. They are automorphisms of the universal cover, and that means they're in the isometry group of this guy. This guy is a symmetric space, and that means that this thing is, it depends how you like to look at it, but I know Kevin would like to maybe look at it in your course as S sub R. The automorphism groups of the upper half plane. I personally like to look at it as SU11. Okay. The SU11, this is the 1-1 situation here. The SU11. Okay. So this is very interesting. You sit down I sit down with my grandson at age 6 and say, look at these matrices, A, B, C, D. He can understand that. But what he cannot understand, and what you don't yet understand, is what are the discrete subgroups of matrices of this form? Tell me. Yeah? Topologically, the genus of the surface, here is compact, determines the nature of the group. You know that, I hope. Right? Topologically, it determines the nature of group. But again, just like in the torus case, the embedding of that discrete subgroup inside of the matrix group has to do with the metric quality of the quotient. The action gives you the quotient, right? It's not just some topology blah blah. The action gives you the quotient. And the moduli space here, the parameter space, again, is determined by complex analysis, is 6G minus 6 dimensional over the radius. Very interesting thing. So you see, even in dimension 2, by the uniformization theorem here that I'm quoting implicitly here, you can always have a constant curvature metric. Then you want to study these things. In positive curvature, you've got the sphere. There's no unit. The sphere is only the universal cover of itself, so that's it. The flat plane covers either rank 1 quotient, so that's C star, or rank 2, so that's a torus. Here you get some parameters. So the parameter space here is just the upper half plane itself. And here, modulo some discrete group. And here, the parameter space is very, very interesting, very, very big. You understand what I'm saying? You have a Riemann surface, compact Riemann surface. It's called Riemann surface because really it's Riemannian surface. It is not, you know, you use this word in complex analysis, Riemann surface is one-dimensional complex manifold. Really, the word Riemann surface means two-dimensional Riemannian manifold, yes, of constant curvature. Riemann was interested in that, yeah? And so he's interested in writing them all down. And now you have something of genus 10, so there are 10 holes, right? Then you ask yourself, how many different metrics do you have up to isomorphism on this thing? The answer is 54 dimensional space. You get it? It's a big, big, we call moduli space of discrete groups. So this problem from various points of view, I have various points of view on this, but for example, Kavon's point of view on this is to study the discrete subgroups in SL2R. Okay? That is also Thurston's point of view on three-dimensional geometry. I taught him this time. Is discrete subgroups of various Lie groups. Okay? You will see why in this thing. And the luck here is the big luck here is, look, luck. Symmetric space, symmetric space, symmetric space. Okay. All of these things are symmetric spaces. In dimension 2, we only need to deal with symmetric space. I haven't said what symmetric space is, but the luck is that this whole theory of classification in dimension 2 degenerates really to this kind of thing. So dimension 2 is a subset of Lie theory. Yeah?
I'm sorry, but what do you mean by discrete Lie group?
I didn't say discrete Lie group. I could have, but I didn't. I said discrete subgroup.
Discrete subgroup is a Lie group.
Well, if you like, it is. It's a zero-dimensional Lie group which is closed in the group of matrices.
Okay.
But it's a discrete set, which is a group. Okay.
So it doesn't have a smooth.
Sure it does. Points are smooth zero-dimensional manifold.
Okay.
No, really. Okay. So everything occurs as a quotient, and the best quotient in life is with a discrete group, because this quotient is a covering space. Right? I beat this into you guys' head in various courses, yeah, as well as you learned a little bit in last semester in topology. Right? I see Avik saying, you're okay? Good. Anybody else? Okay, so now I'm going to do what I started to say. So let us now turn back to holonomy. And this is a holonomy group H, a holonomy group of a connection. And I know it's been a while since we've had a lecture, but you know what a connection is. Holonomy group connection. And at first, at least, with respect to a base point in the manifold. So, what we start out with is we start with a curve, so we let gamma be a closed curve with base point x0 in the manifold. Okay. Now, usually, I mean, when we have a base point x0, we allow closed curves to look like this and so on. We allow that, of course. Yes. But usually when I say curve, I am saying curve to mean smooth. Because you know what we're going to do. We're going to do parallel transport and all of that stuff. So but however, we need to be able to take a curve and then add another curve and take a curve and add another curve, take a curve and add another curve. Say we want to be able to do that, right? Because we're taking a curve, adding another curve, adding another curve. You've done this in homotopy theory, right? You take, for example, if you're computing the homotopy groups of the plane, you take the base of the plane. Here's -1 and here's +1. And you remove, say the plane minus 2 points, -1 and +1. And you say, okay, I see a non-trivial loop about, and here's the base point, x0. I see a non-trivial loop around -1, maybe like that, and I see a non-trivial loop around +1, something like that, maybe, right? These loops around these points, you get non-trivial things. And then, if you're not stupid, you see a non-trivial loop around both, right? And that's how you multiply the two curves, right? And then you get very excited, you have A times B, and I don't know what is A and what is B, but I don't care. And then you get excited and you say, well, what about this? Right? You're very excited when you see that because that's non-trivial. Right? You go around here, go around there, go the other way around there, right? You'd think they cancel out, but they don't. That is non-trivial in the homotopy group, right? These A and B generate the homotopy group of the plane minus 2 points. The plane minus 2 points has homotopy, the free group on 2 generators. Yeah? And they're the generators. Anybody knows, my grandson knows that. I mean, you take a loop around that. I mean, those are the 2 generators. He doesn't know what the free group is, but he knows that those are the 2 generators. And so they are that. And this yeah? So they generate that as a free group on 2 generators, F2. But the interesting thing is, if you integrate a differential form which is closed around such a thing, gamma, the answer, if this is closed differential form, the answer is 0, right? Because the integral is the integral over A plus the integral over B minus the integral over A minus the integral over B, right? So what's happening with homology, yes, when you forget the commutators, is you're integrating, yes? So keep that in mind. Homology cycles are things that are much, much simpler. The homology, from the point of view of homology, this is A plus B minus A minus B here in homology. And here this guy is in cohomology. So if you're thinking homology, cohomology, you've lost this tremendous fundamental group structure. You've killed the fundamental group structure. The homology is the fundamental group modulo the commutator. This is called Hurewicz theorem. Yes, there are higher dimensional theorems than this type. Okay. This is just elementary homotopy theorem. Now, as your author, in this case, Mr. Lee, who was a mathematical physicist at one point, I think, explains very carefully, we need to take a curve, and now to take parallel transport of something along a curve. And then we come here and we start another curve, and we can take parallel transport around here. So you see, if the curve comes and is at least piecewise reasonable here at these singularities, you can take parallel transport of a vector along this curve. Yes, you know how to do that. And then you come to at the end of this little segment where you want to continue on, and you take parallel transport there and continuing on. Right? So even if you have piecewise smooth stuff, you can take parallel transport. Okay? So we can add, so even when, let me put this, pushing my parallel transport, we may add smooth curves piecewise. So this piecewise stuff that we did here with homotopy is also okay for pushing vectors from the base point along by parallel transport along the full piecewise smooth curve. So I hope you understand. You take something like this. Here's the base point. And now I hope I have a little bit of, I don't know. Ah, sure, great. Now I do have pink. Right. So you push by parallel, you push something by parallel transport here, and then you push it by parallel transport here, and you push it by it goes to here, and you push it by I don't know, it goes to here. I don't know how it goes. Because I don't know what the connection is. And I go back here, and look, I drew this purposely in some crazy way. If you start here with that vector, vector v, and you push it by parallel transport along this thing, you get, let's call it P of v. The parallel transport of v around this sum of curves. Right? Okay. So, and it is obvious that, and we'll call this curve gamma. This is gamma. Go around there like that. You get, right? So you have a map, PV of gamma is again, so we take V in the tangent space at the base point, and then you have PV of gamma is also at the tangent space at the base point. At the base point. Tangent vector at the base point, push it with parallel transport, that means you have a connection, otherwise you couldn't do it. Push it with parallel transport, you go around, come back around, you get something else. Yeah.
Why do you know that it's in the, why do you know that it's in the tangent space? Why do you know that it's linear?
What do you think a connection is? The connection is a linear mapping. So what is a connection?
Yeah.
I don't know what you're thinking about, but you know if you have x0 and x1, and you take a curve, and you fix a curve gamma, and you take a vector here, v, and you push it here with parallel transport, v, to here, you know that this mapping along the parallel transport is a linear transformation of tangent space. Right? You just forgot.
Okay.
Yeah, but I did it again. I went there, and then I went there, and then I went there. So I came back to the beginning. So it's a linear mapping. Right? So this says that P gamma is in GL, let me emphasize R here, of the tangent space. I'm reviewing. I've talked about this in great detail before, but I was just speaking English for a few weeks, and all I can think of now is German. I'm sorry. I can't think of the expression I want to say. It has to do with my heart. I really want to emphasize the importance of holonomy. Okay? So the holonomy group, with respect to the connection in the base point, is the set of p gamma. And it's obvious that I can compose because I'm allowing this. I take one gamma and take another one. I mean, I'm allowing piecewise smooth. Right? That's a group. 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 You should be extremely happy with all of this incredible, complicated stuff, connection and so on. And on the end, at the end of the day, you have a group. Right? Cartan defined this in the early part of the 20th century. You should be extremely happy that you start with a connection that you don't understand, and you have a group. Okay? And now, the amazing thing is, this thing is a Lie group. And I'm going to say it is a Lie subgroup of GL of the matrix group, if you like, of the tangent space. I'm going to be very precise about that. But you should be really happy that not only is it a group, it is a Lie group, which means it's a manifold in some way. So that's not bad, right? It's not bad. Yeah.
So you define the holonomy group as the group of all...
I just defined it.
As all parallel transports.
Huh?
As the group of all parallel transports.
And there's the definition.
So you take all the parallel transports and
Take all possible p gamma. So if you like, I'll write it here. Gamma, piecewise smooth, closed curve with base point. With base point.
given a connection.
Huh?
Given a specific connection. So
Yes.
you can have different holonomy groups for different connections.
Yes.
Okay.
It is, I'm glad you re-emphasized that point. I thought I had emphasized it well enough, but obviously I'm not a very good expositor of it. Given a connection, which is a highly complicated thing we don't understand, I have an associated Lie group. Not only a Lie group, it's a group of matrices. I mean, what do you want?
Don't we need to quotient out by something? Because the space of
No.
the curves that...
No.
Well, if you... so take two curves that have a different parameterization or something, would they define different parallel transports?
No quotients.
But you do need some sort of restriction on the curves that you're looking at somehow.
No. Piecewise smooth. Now, I agree. You see, he's worried about different parameterizations and all this stuff. You're worried about, maybe you're thinking about homotopy or something. But the fact of the matter is, in the end, I take two curves. They may give you the same linear transformation. The same linear, no equivalence relation. I mean, what Abik is saying here is a good remark. No equivalence relation here.
Yeah.
Just the same, I mean, all these same things that you're thinking about in your head
Yeah, right.
give you this,
Yeah.
okay, the same, yeah.
Yeah.
Okay. Okay.
Another related question. Why is it not the whole thing? Why is it not all of GLR?
Okay, this is a very good first question. I don't know if you're, why is this not the whole thing? Okay, let's talk, let's make this is all review, but of course this definition depends on x0. Yes, but in the usual way with homotopy, you just go over to x1 and go back. It does not depend really on x0, okay? It's an obvious thing. So it really is, as an abstract group, it's the same. Okay, that's the first point. Okay. And there is a map. So what does it mean? First of all, I want to say what it means, Lie subgroup. Of some vector space. I don't care what vector space. What does that mean? Okay. The first thing it doesn't mean is that it's a closed subgroup. Okay. What it doesn't mean is it's closed. Yeah. So what it means is there is an abstract Lie group let me call it script act H. Now, I don't think I need to say what is a Lie group. I'll say it, but you know, it means it's a manifold. There's a big time word in the definition of Lie group that people forget to say. It is paracompact. Or has countable topology, depending how you want to formulate it. The key issue there is it has only countably many components. Okay? You know, you could just take some discrete set and probably it is, I mean, just some set and it's probably a Lie group in the discrete topology. But I mean here in the topology of this thing, it's an abstract Lie group means it means this thing is paracompact. Manifold with smooth operations. With smooth group structures. Okay. So it's an abstract Lie group and smooth injective homomorphism. So homomorphism say phi of script H onto the holonomy group. Well, okay, I'm talking about the holonomy group in this case. The holonomy group contained in GL. Have you got it? It's a smooth, just say it's abstract. It's an abstract Lie group. So it's wonderful, it's a smooth manifold, it has only countably many components, it has group structure, all the group operations, that means that multiplication or whatever it is, and inverse and so on is you know, it's all smooth. As an abstract guy, it's okay, but the trouble is, it's mapped into GLNR by an immersion, an injective immersion. Okay? Yeah?
So the Lie subgroup is H in this case, like curly H or the holonomy?
You're worried about the word homomorphic?
No, so I'm worried about, so we define the Lie subgroup of GLR.
Okay, I'm sorry, let me be better, didactically better. Lie subgroup H. Okay, the context here is the holonomy group. Right, but it's obvious that it's the general thing. You know all about this because when you were a child, you took a torus, and you took the standard thing, and then you took your rational angle, and you took this thing that's everywhere dense. This thing that's everywhere dense is a trivial abstract Lie group. It's the Lie group R with addition. Right? But the immersion that embeds it, it's also homomorphism. It's also injective homomorphism. It's easy to define it. Right? It's, yeah. This is the way, this is what a Lie subgroup is of GLR. So this holonomy group is one of these guys. Okay? It's not necessarily closed. Okay? Now there are theorems of Borel and Lishnerovich in certain situations where it is closed. So if you ever need this theorem, that it would be closed, in some situation it is, ask me and I'll tell you whether or not it's closed in that situation. Okay? But you do have to have some additional condition. Okay? And somebody, I think it was Abik, I'm not sure, is, of course, this makes sense Let's stop and think. So you have this horrible thing in GLN that's dense or something terrible. And I'm saying it has, you understand the notation H upper 0, the connected component of the identity. That's the usual notation. H upper 0. Connected component containing. You have this horribly dense thing, you don't know what we're talking about. But back there in the abstract group, H script, you know what that means perfectly. It's a Lie group, there's a point in it, it's a manifold, you take that component. Okay? So this makes sense. Okay? Now, you see, this thing here is a normal subgroup of H. Check it. It's unique, so conjugation has to preserve it because conjugation of the identity, G inverse is equal to the identity, and that means that the component of the identity is stabilized by conjugation, and it means that the component of the identity is a normal subgroup. Okay? So that's a normal subgroup. So this thing here is a group. This thing here is a countable group. Because it's in one-to-one correspondence with the components of this manifold. And the theorem that is easy to prove, and this is, I think, what Abik was talking about a little bit, there's a natural map then of pi 1 of the manifold onto H0, H modulo H0, surjective natural map there. So, yeah. It's more or less obvious, right? Because if you have something connected component occur, then you can move it back to the identity, retracting it back to the identity. So it has to be in the trivial at the level of none of that. So really, the interesting thing is the holonomy. Well, and now, of course, Maria is right. She was asking me all about this. So I have holonomy in mind here for everything. So holonomy connected component, and here holonomy connected component. Okay. So the most interesting thing is H0. It's called the restricted holonomy. So for M simply connected, so equal to the universal cover, it follows that the holonomy group is equal to the restricted holonomy group, H0. i.e. you can believe me that if you have a manifold in all this discussion, you might as well go to the universal cover. Yeah. So we go to the universal cover, we kill off the fundamental group, and we have the fact that this holonomic group is connected. Okay. So associated to any connection on any manifold, you have a connected Lie group. An interesting connected Lie group acting on a certain vector, with a representation, acting on a certain tangent vector. Right? Right? By linear transformations. A group of matrices. Right? So Cartan saw this and was really excited, as I am right now. It's very exciting. I mean, right? You just said this awful, terrible thing. You know, you go, I hate this mathematics, I hate this mathematics. And then you get a Lie group, a connected Lie group. Okay. So, I'm still reviewing the lecture. And then you had this professor at Jacobs University who said, well, namely I, said, if you have a metric, a Riemannian metric, for example, or this guy from physics, somebody else from physics, she's from physics, probably other physics people here. Yeah, oh, you're from physics. And you have, maybe it's not positive definite, maybe it's mixed signature metric, maybe we call that pseudo-Riemannian metric. It's okay. You have a non-degenerate guy. If you have such a guy, so you have G, just emphasize that it may be pseudo-Riemannian, so non-degenerate metric, could be pseudo-Riemannian, on M. Right? One of the first lectures, I hope you remember, you probably forgot, I forget almost everything in life nowadays. So you have what we have, a metric connection. Remember what that definition of a metric connection was. There are various definitions of this. The definition that I used in the course at that time was it means if you take the derivative of the metric applied to yz, let me put it like that, you're just differentiating this function, and those two are vector fields. That has to be the same thing as it's the product rule. You remember that, right? And we used some very clever proof of Cauchy to prove that there's a unique metric connection with this property. But there's another nice definition which is absolutely equivalent to this. Maybe it's better, but this was good for Cauchy's nice idea. The same thing is parallel transport is an isometry. We were talking about that.
Yeah, didn't we also require that it's torsion free?
Yes, I'm sorry. So unique. Yeah. Well, what does that say about the Holonomy group? I take a curve, I take a vector, I push it, I push it, I push it, I push it, I come back by parallel transport, I get another thing. This is, I take a vector here, V, and I have the parallel transport along this curve gamma of V. And I have a transformation that goes from V to the parallel transport of V. All right. Well, at each step here, I have an isometry. That says the holonomy group, of this connection is contained in the isometry group, of the tangent space at x0 equipped with the metric g at x0. Not bad. Not only if we have a metric, it lies in some isometry group. If we have a metric, this holonomy thing lies in some orthogonal group. Yes, if for example, if G is positive, so positive, really a metric in the classical sense, then this is an orthogonal group. Now, he's just worrying about torsion here. I mean, I assume I had torsion-free metric if there's no problem. Torsion-free connection, right? It's unique as a torsion-free. There's a unique torsion-free connection. Well, this is really great. Given a metric, let me put the word torsion-free. There's a unique. Put it here. Given a metric, or non-degenerate, could be pseudo-Riemannian, there's a unique torsion-free connection which satisfies this or that associated to it. That means it's in the isometry group. That means this Lie group is even smaller than the whole thing. You understand? In the case of positive definite, this is some orthogonal group. Right? Do you understand an orthogonal group is a compact group? So let me mention fact. So if G is positive definite, then the orthogonal group O of this thing, G of that thing, is compact. Do you know that fact? The orthogonal group is a compact group. It's compact. It's a compact group. This equation, remember, as matrices, is given by A times A transpose. Isn't this the equation? Isn't that the equation for the orthogonal group? Right. And let me just see here what that is. That's Aij times Aji. Isn't that what that, A times A transpose is the identity, right? Aij times Aji is
Maybe all different characters.
what?
It's the
So,
same difference.
okay.
This is delta Ij. I'm not sure how you think, so I just to make sure you think, just to make sure you're thinking, if you have a matrix A, which is in the orthogonal group, and you have this column, and 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 this column, what is the condition that it's in the orthogonal group? The condition is, and you use it all the time with Brown-Schmidt, the condition is that this is an orthonormal basis. Right? The column vectors. Right? Isn't that right? This means each vector has length 1 and is perpendicular to the other vectors. Right? This means that this thing is, maybe this is an n by n matrix. Means this thing is in the n sphere. Isn't that right? It's in the n sphere, unit vectors, right? But with the huge equations because they have to be perpendicular to each other. So we have these equations, right? Well, that's a compact manifold. This is a closed submanifold. So the orthogonal group is compact.
We are talking about orthogonal group in with respect to the metric G, right? So shouldn't there be A?
There is only one metric. So if G, oh, I see what you're saying.
A, G, A transpose.
He's asking a question, which is probably good, I don't know. So I'll have to answer some question. Okay. What was your question?
So shouldn't we have A, G, A transpose equals identity?
Okay. There is only one positive definite metric on a vector space, up to conjugation.
Yeah.
Well, I just wrote it down. I'm finished. He was worried that I took a special metric, namely scalar product, right? You understand? If you have a positive definite bilinear form, well, maybe that, I don't know. I always worry about, can't you diagonalize it?
Yeah.
Okay, well, okay, I don't worry about 1 or 2 or 7. Okay, it's the same thing, right? Right. Okay. Okay, good question. So, okay, so we're in that case, the holonomy group, in the case of a positive definite metric, a Riemannian manifold, the holonomy group is a subgroup of orthogonal matrices. It's a subgroup of a compact thing. This is a very simple-minded situation. It's wonderful. By the way, I hope you know that if these physics people here wanted to do SO13, right, or SO31, well, in relativity theory, you usually do that, right? Right? SO31 or O31. You understand what I'm saying when I say that? I mean, every physics person, Abik doesn't like me for saying that. You know the physics people, at least I'm trying to make physics people happy here. Come on. This, okay, there's only one, from my point of view, there's only one quadratic form of signature 1, 3. By the way, I put the negative vector first. For some reason, I put the 1, so that I really mean, I mean here, 0, 1, 3. Okay? I don't know. Okay? There's only one such thing up to some eigenvalue or something, right? Or we can have some square root transformation or something. You're okay. Okay. Yeah. This group is very non-compact. Okay? And that's the whole point, because and then you will have light cones and all this stuff I'm talking about. Okay? This group is very non-compact. So if you have a real, an honest-to-God metric in the math sense of linear algebra -1, right? It's positive definite. The group is compact. The Holonomy group is compact. But if you have pseudo-Riemannian setting, the Holonomy group may be non-compact. Okay. Well, all of this Holonomy stuff, to get a compact group or all of this stuff, all of this, we needed a metric. In some sense, right? We needed a metric. So as maybe one of my last remarks today, I just want to point out, you do have a metric. Now, this is a point that I forgot to make earlier in the course, and I think is worth underlining. I'm going to make a construction. Construct a metric from a holonomy, from a connection. Using holonomy. Okay. Construct a metric from a connection using holonomy. Now, I really wanted to explain this to you because the construction is very easy. Okay. Second of all, the paper where this construction first appeared is due to a mathematical physicist from Hamburg. Surprisingly enough, it was published in 1973. That is not very long ago from my point of view, right? I mean, this whole theory of Cartan is very long time ago. So, and this construction, as you will see, is trivial. Okay? But it emphasizes that you should sit down and think slowly about everything, and you may end up, very likely will end up, understanding something new. You know? Have the courage to do that. So this is the following. So suppose the holonomy group, I don't care whether we're in the universal cover or not, is contained in an orthogonal group. Mixed signature or not. Almost finished. Now, suppose it's an orthogonal group of mixed signature now. Okay. Then take, so a group, say, of G. Okay. Yeah, come on in. Sit down. Joyce, you might learn something.
I would like to, yeah.
Am I going over again? Okay, here is x0, here is x1, here you have G. Guess how you're going to, let's call it G equals G of x0. How would you define G of x1? How would you define, yeah,
Use Taylor transposed?
you just proved the theorem that was proved not so long ago. Very nice. Take any curve, right? Take a vector here, V. Take a vector here, W. Push back by parallel transform, V hat VW. Holonomy of G of x1 of VW is defined as G x0 of V hat W hat. Yeah? Just push back where you know it, define it. And just check that this thing that you've done, defined, is the metric connection, is a metric connection for this. For this metric, the given connection is a metric connection. Okay, so it's very, very close, the two things, if you use holonomy. And of course, you need this fact that I've written there, that the holonomy is contained in an orthogonal group, because you need to find the metric somehow or another. Okay, I'm sorry I've gone over. I have to apologize to the colleague. So